All right, welcome back. This is Lecture 3C of Bayesian Psychometric Modeling from Fall 2024 at the University of Iowa. You know me, I'm Jonathan Templin. This is a recorded lecture, not a live one, so it should be a little bit better, but we'll see. And if you're watching this on YouTube, which I'm guessing you are, hit that like and subscribe button, because I think I'm supposed to say that. If you do that enough, maybe I'll get some merch. Who knows? Anyway, I wouldn't wish that on anybody. Let's talk about today. All right, we're going to talk a little bit about Bayesian model fit and model comparison methods. These are important to understand whether or not the model that you've chosen fits the data in an absolute sense, and whether or not, if you fit more than one model, which model seems to fit best relatively. Now, we can use these methods to help inform us whether or not our choices of prior distributions and hyperparameters for priors are working. Think of the case from a few lectures ago where I put informative priors on regression coefficients. Those informative priors force those coefficients close to zero, making the residual standard deviation quite large. If we use some of these methods, we would be able to tell whether or not that was a good idea, how closely our result fits our data. So let's dive in. Okay, there are two types of methods that we'll talk about today. One is absolute model fit. That is, how well your model fits the data it was applied to. The methods that we will talk about today are something called posterior predictive model checks, or PPMC. Then, if you'd like to compare different models, we will come up with methods or describe methods in the latter part of the lecture to go and gather information as to which model might fit the data better. These methods fall under a broad heading of information criteria. In Bayesian sense, there's recent work where one is called the WAIC, or the widely available information criterion. And the other set is part of a group of methods called leave one out methods. These leave one out methods originated in cross-validation, the idea that if we left one observation out from a sample, how would we be able to predict it? All right, let's dive into PPMC, or absolute model fit. Remember, the term absolute model fit basically tries to answer the question, does my model fit my data well? So this is for a specific piece of model and a data set. It's important to establish absolute model fit because if you have, let's say, a set of competing models for the data, A, B, and C, and only A and B fit the data, but C does not, you shouldn't even consider model C as a potential for selection and describing your results. So the overall idea in posterior predictive model checks is this. If a model fits the data well, then simulated data based on this model will resemble the observed data. Right? So the idea in posterior predictive model checks is to simulate data based on model estimated parameters, and then to summarize that simulated data and compare those summaries with the original data. What do I mean by summaries? All right, so let's think about what the ingredients happen to be. We have our original data, right? So in our case, in this lecture 3 sequence, we've used this data set from UCLA, the diet data set, where we were predicting the weight in pounds. Well, weight in pounds is our outcome variable, so we should describe how it looks overall, and our model should somehow come up with results from simulation that resemble it. So we would take that original data, in our case, weight in pounds, and we might characterize it by some set of statistics, like we might talk about its sample mean, or its sample standard deviation. Or perhaps if we have more than one variable, we might talk about the covariance or correlation between items. Then, what we'll do is we'll estimate our model using STAN, and for every outcome draw in every sample from the posterior distribution, we will then create data that are simulated as if that sampled values of parameters from the posterior were the true values. So basically, if you think about the process of sampling in Bayesian, in our Markov chain, we sample parameters from our posterior distribution. In our example, we had 6 regression coefficients and 1 residual standard deviation. Every successive iteration will have potentially new values for each. So what we end up doing is taking those new values, generating a data set that has the same number of observations as our original data, and calculating the same summary statistics on that generated data set to come up with what's called a predictive distribution of those statistics. I'll show a little bit more as we go forward here. So let's put this into context with our example. Here we have our linear model with the diet data where we're predicting latent pounds. It has an overall intercept, a main effective height, a main effective diet group, and a height by group interaction. Along with E having a residual standard deviation. We estimated this in Model 6 of Lecture 03B. This was where we had normal distributions for priors for each of our coefficients with a variance of 100, and an exponential prior for our residual standard deviation with a hyperparameter of 0.1. So there's our model estimates. That's the result of the Markov chain. Those are posterior summaries, remember. But like generated quantities that we saw at the end of Lecture 3B, we're going to use generated quantities to use draws or samples from the posterior distribution to create these simulated data sets. So here's the process. We will select parameters from a single iteration of a Markov chain. Using the selected parameters of the model, we'll simulate a data set with the same size, number of observations and variables. And from the simulated data set, we'll calculate the summary statistics that we selected. We will repeat steps 1 through 3 for a fixed number of iterations, or perhaps across the entire Markov chain itself. And when we're done, we will compare the position of our observed summary statistics, this is from our observed data, to that of the distribution of summary statistics from the posterior predictive process. If our summary statistics are right in the middle of that posterior predictive distribution, we will say our model fits the data quite well. But if the observed summary statistics are far off from the predictive distribution, we will conclude that our model doesn't fit the data very well. So let's keep going. Here's an example. I'm going to make this example without Stan, and then I will show you how to implement this in Stan. So for our model, we have one observed variable, which is weight in pounds. I'll call that Y. And now I want to note that our observations in the design matrix X, these are our predictive variables, are not modeled. Right? They're not part of our analysis. They're not part of our model. So we couldn't create these variables even if we wanted to, because we have no idea as to what those values would be. We don't have a kind of a statistical or stochastic assumption about them. So we don't know. But let's take a look at what a posterior sample might look like. So here we can take the draws matrix where we just have beta and sigma. And this is from a sample where I did 2,000 post-burn-in iterations. You can see from this summary table my R-hats are all 1, so we have converged Markov chains. So we'll dive in with these 2,000 iterations. This is one sample, draw number 1 of that posterior. And here are the values of each of our coefficients, along with the value of our variant, our residual standard deviation. And you can see, because we ran 4 chains, there's 8,000 of these values in total. So you can see it says with 7990 more draws. Again, draw is synonymous for sample. So let's take one draw at random. So let's take here, this is a process to figure out which iteration to go and grab at random. We took iteration 7,745, which had values of this right here for our coefficients, and a value of 11 for our residual standard deviation. So now in PPMC, our process is to treat these parameter values as the true values and to generate a random data set, assuming these were true. Right, so I'm going to put our beta coefficients into a vector here. Right, so this is our vector of coefficients. This may look like what we have in beta in Stan anyway. And then we'll take sigma and just take its value. And here that means if I took my design matrix X and I multiplied it by our beta vector, what I would end up getting is the predicted value for each person, assuming that these beta coefficients were correct. Right? So here, this is this predicted value for each person. If you remember in our Stan model, going to an example here, we say that Y follows a normal distribution. The mean of it is X times beta. So here in our example, beta is a vector of numbers from this draw 7,745. Those are the values. So those actually form the mean of a normal distribution. Similarly, in our model, we say that sigma is the standard deviation of this normal distribution for our data. So we take our value for sigma from the posterior, from iteration 7,745, and we use it as a standard deviation. And in R, our norm right here will generate data with a sample size of 30. Each value of the conditional mean is a different bit of the sample. Pardon me, there's 30 different conditional means here, and sigma as well. And actually, let me just go and execute this, run this in Stan real quick to flip back and forth, because I think this is an important concept to come across. This will just take a moment here. This is where idle small talk happens in class, so just pretend I'm having small talk. Could have done this earlier, but evidently I'm not familiar with recording lectures without people present. So again, these are our values of our linear model. We have a predictor matrix, and we estimate Stan. This is where we take our posterior sample. Right here, our sample iteration, this will probably not be 7,000. And here I'm going to actually say this is. So we'll just take that 7,745 just to match our slides. These beta values are close to the same. Yes, actually they're very close to the same. So here's our beta vector. Actually, they are the same, thankfully. So that's our beta vector. This is our value for sigma right here. So this conditional means part, where I'm multiplying our predictive matrix by our beta vector. Remember, this matrix is size n rows by p columns, or 30 rows by 6 columns. Beta vector is a column vector that has 6 rows and 1 column, so we can make a matrix multiple out of it. And when we do that, these are the predicted values for each person's weight. Right? This is our outcome y, assuming that the beta coefficients that we have here, this beta vector, were the true values. So now we can generate normal, random data from the assumption of our model. We assumed that y was normal, where the mean was this conditional mean based on our predicted value and a standard deviation of sigma. So if we do that, here are some normal values, right? There's 30 of them. I can just keep sampling. I can keep running this. So each one of those is a sample. You can see the numbers bounce around quite a bit. That's what we want. We want this process to resemble our model and our data. So now we can create our simulated data, and this is an example of our simulated data for this single iteration from the Markov chain. There's our histogram of it. All right, moving forward, let's imagine that we want to evaluate whether our model fits our data with respect to the sample mean and the sample standard deviation. These are the two statistics that we'll evaluate. Now, our sample mean for the data itself, our simulated data's mean happens to be 170.7093. It's a little bit different than the slides in my R because I've done that simulated process multiple times, but you can get a similar number if you keep doing this. The simulated standard deviation happens to be 48.93. Right. Now, if we were to look at the mean of our diet data, the actual mean was 171, and the actual standard deviation was 49.5. So for this one simulated, sample posterior, one posterior sample of beta, and this one posterior sample of sigma, our simulated data had a mean of 170.7093, and our simulated standard deviation was 48.93. Our overall mean of our data, the observed mean, was 171, and our observed standard deviation was 49.5. So we're kind of close. We're a little bit low on either, but that's okay. We would expect it to not be perfect. Right. So now let's repeat this process, but let's loop across all of the iterations. Right. So now, instead of doing one at random, I'm literally going to go through each one of the iterations. I'm going to create an object in R that will store each of those iterations simulated mean, right? So for each iteration, so remember there's 8,000 total iterations. That means I'll have 8,000 data sets. That means by the end of this, I'll have 8,000 simulated means and 8,000 simulated standard deviations. So now, run this process. It takes a little bit of time. But now instead of having a single simulated mean, this is what we call the predictive distribution of where the mean of weight should happen to be. Right? So, taking a look, this is the predicted distribution of the mean. This is the predicted distribution of the standard deviation. So now we can actually compare our simulated values with that from our real data. So here in the diagram on the right, you can see what we have here is our predictive distribution of the mean, right there, and the line superposed on top of it was where the sample mean happened to be, 171. And we can see that the sample mean shows up in the center of the predictive distribution for the mean. That's a good thing. That indicates that our model thinks the mean should be somewhere around the histogram. Right? Our model thinks the sample mean should be somewhere in these sampled values, whereas the yellow or the orange line here indicates it's right in the middle of it. So we have, with the sample mean being plausible for our model, indicates that we have pretty good model fit with respect to the sample mean. We can do the same thing with the standard deviation. Remember, the histogram itself represents our predictive distribution. This is from the simulated data. Right, there's 8,000 standard deviations, one from each of those 8,000 simulated data sets. And the orange line right here in the middle shows you where the data's observed standard deviation is, slightly less than 50. And again, because that standard deviation is in the center of our predictive distribution, we can show that our model fits the data quite well with respect to standard deviation as well. So again, another very good thing with respect to our analysis. So posterior predictive model checks are incredibly useful, right? They're an easy way to provide a visual summary to determine if a model fits observed data. And I would say that they are the main method of assessing absolute fit in Bayesian models. Absolute fit, remember, is used to assess if a model fits the data directly, rather than a relative fit, which is two competing models for data itself. Now, there are a few drawbacks to PPMC methods. Almost any statistic can be used, and it turns out some are quite much better than others. What I mean by that is that in some cases, certain models will always fit the data with respect to some statistics. I'll give you a quick example. If you're using a latent class model, which is a sort of classification-based model, it's sometimes thought of as psychometric as well. And you have, you have a complicated, you maybe have 4, 5, 6 classes of data, and you want to use each, and you have a set of items, let's say a set of variables, say 10 variables, 10 collected variables, 1,000 people, latent class model with 3 classes, and you use the mean of each variable. It turns out that latent class model will almost always fit the mean well, even if it doesn't fit other statistics well overall. So you have to have a little bit of understanding of model characteristics to know which statistics are better than others. This actually can be used to hide model misfit if you're not careful. So as a reviewer, if you're looking at Bayesian papers, Bayesian methods and papers, you want to have the authors be very, very, very explicit as to which statistic was chosen, why, and what would we expect the result to be. The other part is that there's no easy standard to determine how much misfit is too much. Right? We have this predictive distribution of each of the statistics of interest, and we have our observed variable as a sort of a quantile in that distribution, right? If it's in the center, that's great. If it's in the tail, how far is too far? And then finally, depending on the model that you're estimating, posterior predictive checks may be overwhelming to compute, right? It's a very computationally heavy process to simulate data for each iteration, but there are ways to make it a little bit easier. I'll show a little bit of that as we go forward as well too. So next, the other thing we can quantify from posterior predictive checks is the concept of a posterior predictive p-value. Now note, this is not a p-value in a frequentist sense. but this talks about literally how far our observed data is, basically the percentile rank of our observed data with respect to the distribution that we have, the posterior predictive distribution. This will tell us a bit of what proportion of predictive draws are above or below our current data. So for instance, if we look at this plot, right, our sample mean is the yellow line right here in the middle. The posterior predictive p-value for it would be something like 0.44 or 0.45, right? It's somewhere where a little bit, maybe a little bit less than half, or maybe a little bit more than half, or below it. Observations of the posterior predictive sample mean is below it. If this value happened to be in the tail, let's say over here on the left, your p-value would be 0.01 or 0.02, indicating, yeah, there's very few predictive values that were lower than it. Similarly, if it were on the right here, if it's like 180, the p-value would be 0.999, be very close to 1, indicating that nearly all the simulated data means were below it. So the posterior predictive p-value, turns out for the sample mean, was 0.4425. That is a number very close to the center of the distribution, so we like that number in terms of model fit. For the standard deviation, it happened to be 0.50325, again indicating that about 50.325% of the simulated data set's standard deviations were lower than what we observed in our data. So had either of these values been close to 0 or close to 1, this would indicate that our model is not fitting the data well for these two sets of values. All right. Let's move forward just a bit here and play around a little bit with this information for a different set of priors. So here, hang on one second here. Let's compare our model fit where we had a prior, our current prior happened to be for each of the coefficients, a standard deviation of 10 and a mean of 0. And then our sigma parameter had a value of 0.1 for its hyperparameter. Let's compare that to a model where our standard deviation is 1 for each of our coefficients, and our sigma parameter has a hyperparameter value of 10. So much more informative priors, right? So let's build this sample right here. So let's check convergence. The maximum R hat turns out to be 1.00, so it converged. Let's take a look at the summary statistics. Remember, this is a result where we see right here our beta coefficients look nothing like our real data itself. And our sigma for this is also quite low, quite small. So here, what I wanted to do was create and take a look at our posterior predictive statistics for it. So let me grab my syntax from before and calculate it for us here. Let's do this right here, posterior samples. I'm going to have to copy some syntax here and put the syntax right after model 06B. And here, our posterior sample is 06B. And let's calculate all of our sim mean and sim standard deviation from it. And now let's take a look at our summary statistics. There we go. This is our posterior predictive distribution for the mean of our data. So the yellow line is our sample mean, but the mean of our data from our crazy informative priors for each of our samples in the Bayesian statistics is nowhere near this yellow line. So this posterior predictive p-value would be like essentially 1. Right? No simulated data set had a mean anywhere close to that. That indicates our model isn't fitting very well. That's a bad idea. Bad sign. Probably our priors are the problem here. We do the same thing for the standard deviation. You can see it looks a little bit more reasonable. Hey, that standard deviation is right where it needs, close to where it needs to be in the center. And this is one of those where knowledge of the model itself comes in handy, because this posterior standard deviation right here, the model itself, because if you look at our summary statistics, because our sigma adapted to having low values of the mean right here, right? It reflected, it's plausible the data set had a standard deviation, or the height variable, the weight variable had a standard deviation that was within range of where the observed data happened to be. But that's just the consequence of this type of model. You know, if you mess up, if you create problems on your regression coefficients, remember that's the mean side of the model, you don't predict that well, turns out the standard deviation side goes up. When it goes up, it's plausible the data are in the model itself. This is part of the reason why in intermediate statistics you never discussed model fit, because most always linear models fit the data with respect to the variance. Now, in a Bayesian linear model, it may not fit the data with respect to either. In fact, if I further increase the prior for sigma, you would expect this to be less and less looking like sigma itself. But that is sort of the case. And that's where posterior predictive p-values can tell you whether or not your prior distributions seem to work okay. So it turns out my process in building this whole loop was just built to be kind of an exercise in getting you to understand the concepts of posterior predictive model checks. We can use that generated quantities block of Stan to do the sampling for us, which is excellent. So here's some Stan code to do just that, right? So what do I need to do? I need to create for each person a set of predicted value, a vector of predicted value. So y predicted here is a vector. It's size n, same size as our data. And what is it going to be? It's going to be our design matrix, which is fixed and submitted to Stan as data, times the current values of the beta coefficients from that step of the chain. Then I need to create a vector, in this case what's called an array in Stan, to store simulated data. And Stan actually has a function. For every distribution in Stan, not only do you have a likelihood function version of it, you also have a random number generator. So normal underscore RNG stands for normal random number generator. And what you have to provide to it is the mean vector, in this case our predicted values, and a standard deviation, in this case sigma. This sigma is the current value of sigma in the Markov chain also. Now what we would like to keep track of is calculated below. So for instance, we have our mean y. Our mean y is constant. It will be the same for all steps of y. It's just literally the sample mean. Similarly with our standard deviation of y, it's constant throughout all steps of the chain. And finally, what we can do is calculate a mean that varies from iteration to iteration based on the values of y rep. So basically what we're doing is we're taking y rep. Because it's an array, we have to convert it to a vector. That's some of the Stan notations, details that are sort of nuanced that you can see in the Stan user guide. But we're going to take the mean of that. So mean y rep happens to be the mean of our posterior predictive samples across each of the posterior predictive simulated data sets. The mean of the posterior predictive simulated data sets. So we'll have 8,000 means at the end of this. We can also have the standard deviation saved as well. Again, that's the standard deviation function of taking our simulated data and converting it to a vector. And then finally, to calculate the posterior predicted p-values, what we can do is look at the proportion of, and actually I realize I've been describing this a bit backwards, the proportion of observed values, no, I've been doing it just right. The proportion of times our simulated data are greater than our mean y, happens to be mean GTE. That's what we can count. It's going to be an integer that's between 0 and 1. an integer value that's either 0 or 1. This returns an object that's, if it's true, it's a 1, and if it's not true, it's a 0. Similarly, with the standard deviation, we can calculate that as well. So now, when we calculate these values, we can calculate the posterior predictive distributions directly from Stan and have them outputted in our data set as well. And here's what we have. You can even you can see here our mean overall from this analysis. Our posterior predictive mean, the mean of all of our simulated data sets, was 171. The standard deviation was 49.5. We can see the posterior predictive p-value for the mean is 0.443, and the posterior predictive p-value for the standard deviation is 0.502. And once again, I transposed what the p-value is. It's the proportion of draws greater than where the mean happens to be for each of these, right? So this one right here for the mean, 44% of the sample draws were bigger than the mean itself. So there you have it. So Stan is very helpful in calculated generating quantities, and we can do most of our work to assess model fit directly in Stan for our model itself, which makes the posterior processing much easier. We can also do similar methods for relative model fit. Okay, so that is posterior predictive model checks. They are powerful ways to check if models fit the data. Believe it or not, they can even be used somewhat in frequentist statistics, and I find them to be much more informative than our typical model fit statistics, in that they sort of show how bad our data look if we were to simulate it from our model result. Relative model fit is a bit different. It is the process for comparing between two different models, competing models on the data. This process will not tell us whether one model fits the data in an absolute sense better than the other, but it will tell us which model seems to be best at describing the data that we have. So if we were in a non-Bayesian methods class, you might have heard of methods for model comparison that fall under the heading of information criteria, sometimes AIC or AKIK information criterion, or BIC, the Bayesian information criterion, sometimes called Schwartz's information criterion, have been used. There are a number of these. Typically, we would run a set of models, model A, model B, model C. Each model would then output one of these, each of these values. So there'll be, if there were 3 models run, there'll be 3 AICs. And it seems pretty weird, but we just pick the model that has the lowest AIC, BIC, and so forth. Bayesian model fit is very similar. We're going to calculate an index value that will look like an AIC or a BIC, and then we will pick the model with the lowest index. Right. Now, I will note in relative model fit methods, you can sometimes have discrepancies based on indices. So, for instance, if you're in a frequentist world, you may have fit 3 models. Model 1 may be preferred by AIC, and Model 2 may be preferred by BIC, and in such situations, you may not know what to do. The same thing happens in Bayesian methods. However, the newer methods also provide a bit of uncertainty estimates for the AIC, for their versions of indices. So that helps you describe whether or not there's strong information that suggests one model is more preferred than another. Let's keep going. So these recent advances, I say this is recent, I mean this is within the last 10 years, these indices have really come a long way. Basically, the idea is we're using Bayesian model fit indices that are tied to making cross-validation predictions, right? Cross-validation is the process where you estimate a model with one part of your sample, and then we use your model estimates to predict the part of your sample that was left out. In the Bayesian statistics we're going to talk about, we talk about model fit with leaving one observation out, or LOO. So basically, we can think of, if we were to do this process, we could estimate, in our example, we had 30 observations. Let's remove one of the 30. We have 29 remaining. We fit a model to 29, and we calculate how accurately we create a predicted value for the 30th with it not being part of the model, right? Now, those statistics that we can calculate for accuracy could be a whole bunch of different ways, right? We could talk about discrepancy between predicted value and true value, or we could even talk about the log likelihood of the missing observation conditional on the model parameters that were estimated, right? But we would want to do this for all observation. Now, you can tell with 30 observations, it might take some time. We'd have to fit 30 different models. It would be difficult. If that's only with 30 observations. Imagine if we had 300,000 observations, what would happen? So newer methods that have been developed try to mirror the leave one out approximate predictions, but approximate these so that make it a little bit easier computationally. The first version of Bayesian model fit, which was developed in the late 1990s, was something called the deviance information criterion. The deviance information criterion did not follow what we're talking about today with the WAIC and LOO, but it was calculated based on two quantities, right? The estimated number of parameters was a penalty term, and this d bar of theta, which is effectively the average value of the -2 times the log likelihood of your data, conditional on model parameters from that iteration of the chain. So we use this to calculate estimated number of parameters and likelihood, and then we would compare DIC across different models. Here, DIC has really fallen out of favor more recently for many reasons. Number one, it has issues when parameters are discrete. So if you had a discrete parameter, a classification, let's imagine you're classifying people into one of two groups, the average, the log likelihood of the data computed at the average of the parameters is not part of the sample space, because the probability someone is in each group would represent the average for the classification variable for a person, but that average is not a 0 or a 1. So that causes an issue with DIC. It's also not fully Bayesian. You are computing point estimates of average parameter values to make it work. And finally, it can give negative values for estimated numbers of parameters in the model. Not great. Besides, the estimated number of parameters concept itself was somewhat fuzzy because parameters in Bayesian, because of the way that we use prior distributions, it's sort of almost like how much information a parameter may give. And if you have really informative priors, it may not give much information at all. So it's an interesting concept, but DIC, still you see it used, but typically what we've been moving toward are sort of these other corrections. The WAIC, which is either widely applicable, or Watanabe Akaike information criterion from 2010, corrects some of those problems. It is fully Bayesian. It's asymptotically equivalent to Bayesian cross-validation, and it is invariant to parameterization of the model itself as well too. Now there's another method which is called leave one out. Leave one out. Now actually in STAN we use something called leave one out via Pareto smoothed importance sampling, so it gets even more complicated. I'm not going to teach you the ins and outs of what all those words mean. I'm going to teach you how to use this though. But what it does. Leave one out. Remember, leave one out is the process of cross-validation, where we estimate a model with all but one of the observations, and then we take our model parameters and do something to predict that observation or calculate its likelihood itself. So what LOO does, because there are so many different models we'd have to run to make leave one out work well, this Pareto smoothed importance sampling step attempts to approximate the process of leaving one out in cross-validation. It gives a finite sample approximation. It can be implemented in STAN, and it quickly can be used to compare models. And it also gives warnings where it may not be valid or reliable to use, in that this approximation may not be very good. The details themselves are quite technical. If you'd like to see them, you're welcome to see this preprint at Archive for the paper that underlies it. It's from 2017. But the big picture is that we can compute WAIC or LOO, leave one out, via a package named LOO, which comes from STAN, and it gives variability, and the LOO estimates themselves give variability for model comparisons, which is really important to determine which model seems to have the best information. So let's talk about how to build this. Both of the methods that are used, WAIC and LOO, the core of them is the log likelihood of the data conditional on the model parameters. Right? So remember, the log likelihood takes the distributional assumption, plugs in our observed value, plugs in our predicted value, and sigma, and it calculates the height of the curve. Right? Now, as you know, our predicted values change from iteration to iteration because our sampled beta values change. Similarly, our sigma values change. So what we're going to do is we're going to keep track of the observed log likelihood for each person across each iteration of our Markov chain. It's yet another generated quantity. So now what we've done is we use this function called normal LPDF, which is short for log probability density function. It's our log likelihood of the normal distribution. We provide the y value for each person in it, and then we make it conditional on a mean. In this case, for each person, it's their predicted value. That predicted value is formed by that person's design matrix rho times our current beta coefficients. And our standard deviation for it is our residual standard deviation from our Markov chain. So using the LOO package, we can calculate WAIC. What we have to tell it is using the WAIC function. Of course, I clicked the wrong place. Right here. The WAIC function, we provide it with our draws of our log-like feature, and it calculates it. And our WAIC happens to be 2.18 with a standard error of 13.6. This is for the model with, I would say, fairly uninformative prior distributions, our first model. Now, if we compare that to our model where we have very, very informative prior distributions, we will see here that that model provided the WAIC of 740.6 with a standard error of 61.9. What we want to pick is the model that has the lowest estimate of WAIC. And in this case, that's the model with uninformative priors that fit our data better. We saw that with our posterior predictive checks, but it also fits better in a relative sense as well. Furthermore, if these two numbers were close and we would have a tough time deciding, we might look at how much error there was in each estimate. So what this tells us is that the WAIC has 218.9 with a standard error of 13.6. You can think about how confident we are with that number with how large the standard error is. If this other value estimate was like, say, 219, but its standard error was 61, we would have less belief in it than we have in our current, our other model, the 13.6 standard error. And finally, you will get Stan also gives you a recommendation as to whether or not these the number of parameter predictive estimates are bigger than 0.4. This is technical information. I'm not sure I fully follow it either, but it tries telling you that, oh, a certain percentage of these are in a bad zone. We recommend trying leave one out. Okay, no problem. Leave one out, we can do that. So we skip over. It turns out there's a function called LOO_compare. And here, if you wanted to see the LOO for each one of your samples, it turns out all you have to do is give it the LOO function. And as long as you have a variable named log-like in your generated quantities, it calculates it for you. So here we have the uninformative priors. We take its LOO. We have the informative priors with their LOO. And we can put them in a function called LOO_compare, LOO compare. And the value that has the lowest is the one we would pick. That's the uninformative priors. It gives us the difference in expected log posterior density for informative priors. It also tells us the standard error of the difference as well too. So here, the standard error tells us basically how much we can put a confidence or certainty around this difference. Right? So if this difference is smaller than the standard error, we would say, yeah, one is preferred to the other, but it's uncertain, quietly uncertain. But here, that's not the case. We have a difference of negative 260.2 with a standard error of 33. Our difference is quite large compared to our standard error. So basically, we would think that this model seems to fit much better, the model with uninformative priors. Now, one thing I did want to show you a little bit more of was what this LOO output looks like. So here, the LOO output from Stan for any one model by itself just calculates a table just like you saw with WAIC. This LOOIC is the statistic of measure. It also tells you which diagnostic values, basically how many are in a range that are good or bad, right? And so 29 of our values were good, one of our values was bad and none were very bad in this model. So if they're very bad, if for instance, if LOO is bad, it's not clear what to do next, but you shouldn't give much belief into the result. Now here's that same value for LOOIC, right? You see our difference. And here it tells us all Pareto K estimates are good. So before we had one that was bad out of 30, and now we have all that are good. But that is what is happening to give us the difference that we're looking for. And so LOO is, I would say, usually preferred over WAIC. So here's some general points here. WAIC and LOO converge as sample size increases. So WAIC you can think of as the asymptotic value of LOO. This in and of itself is an interesting part. That means typically what I would typically do with my own analyses is to leave one out, almost always. But WAIC you see sometimes, and I'll hold that on there as well, in particular because there may be cases where LOO doesn't work because of the sampling method. The Pareto smooth importance sampling may have too many bad values, and WAIC you may have to fall back to. There are some other caveats as well. Latent variable models, which will be the bulk of this class after this lecture, have interesting challenges in Bayesian. I'd say that this is an active area of research that needs more exploration. And basically, the idea is the latent variable, what do we do with it? In a Bayesian model, we typically think of everything as random. In a non-Bayesian model, we think of only the latent variables are random. How do we measure things with that? It's difficult. Similarly, if you have missing data, you will also have problem as well. You can actually think of latent variables as missing data in many cases. Oh, and on that note, quick plug, next semester I will be teaching a class on missing data, which includes latent variables. So if you're interested, sign up. Finally, LOO is recommended, but providing both is also appropriate. So you will see both in literature if people are using Bayesian analyses. You'll also see DIC instead. But just remember, I prefer LOO first. If LOO doesn't work, WAIC is next. But DIC is sort of no longer used, or shouldn't be really used as much anymore. All right, so to wrap up, this is the culmination of a 3-part lecture plus example using linear models that I wanted to use to show nearly every part of a Bayesian analysis. Those parts include MCMC specifications, prior distribution specifications, how to assess MCMC convergence, how to report MCMC results, how to tell if the model fits the data absolutely, and how to tell which model may fit the data if you have more than one model that you've estimated. All of these topics are going to be with us throughout the rest of the class. So if you're not fully familiar with each of those, that's okay. You're going to have lots of repetition as we go forward. But next, we're going to talk about psychometric models. We'll actually put Bayesian together with psychometrics, and that will be the remainder of what we do. So thank you for listening. If you have any questions, don't hesitate to reach out. And I hope that you've enjoyed this part of Bayesian. I think this is really an interesting topic and a really interesting class. Take care.